Hey everybody, this is Larry. This is day 30th of the June Leetcode Daily Challenge. You've made it if you're here. The last day of June. Hope you did the entire month. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. The lowest common ancestor of a binary tree. So this one is a very well-researched problem, or at least at some point. I don't know if this is a well-known thing because people keep on telling me about this. But I actually, a fun fact or quick little story is that my professor in college actually taught this as part of the algorithms, and it actually goes into that linear time processing, constant time query lookup, algorithm, which gave birth to a lot of competitive algorithms that are kind of have names that when I learned it did not have those names back then, like sparse table. What was the other one? There are a couple of things I forget what they are now, so maybe I made that up. But in either case, in this particular problem, let's take a look at it first. Seems like you only get one query, so you don't really have to be that optimized, and you can't really be that optimized anyway, to be honest, because because you have to look at every I was gonna say you have to look at every node to kind of find the items, right? Because you're not given the node. Oh, actually no, I was wrong. You are given the nodes themselves. So but I think in the worst case it's still gonna be linear because you have to look at the entire tree. Like if you have two linked lists essentially that meets up at top, I don't think there's any way to avoid it. So yeah, so it's gonna be linear anyway, but it is a fun algorithm. If you want to read up on that algorithm, the O of N algorithm is actually pretty cool. Pre-processing and O of 1 querying, and you can even do the you can do an N log N with O of 1 querying pretty simply as well with just sparse tables. So anyway, that's kind of a fun trivia for those of you who are into the harder competitive ones. Otherwise, it's totally unnecessary. But I am a big fan of LCA, and as a result, LCA does have a soft spot in my heart as an algorithm. Anyway, so yeah, let's take a look at this one. So you're just given two nodes directly, even though the input doesn't look like it. I thought you have to search for it, which is why I was a little bit whatever. But yeah, so then here, what can you do, right? I mean, I think the straightforward way is the O of N space way. Yeah, and I guess that's. I don't know if you can do any better. I don't think you can, only because in this particular case, even though I said that you didn't have to search for them, I think you do anyway, because you have to find the parent and stuff like that. Because just to give an example, if you have a P node and a Q node with just like a common parent, there's no way of you to know without kind of traversing the tree. So you still have to find the nodes. So that's one. And then the second thing is basically you have two paths, one to P and one to Q. And there are a couple of ways you can do it. You can do it forwards, you can do it backwards, you can do a sort of and then just a linear, slide through the through in a way or whatever. I think that's what I'm going to do because I think all these cases are O of N anyway. And there are some it depends on how you want to optimize for this problem. There are a couple of optimizations here and you can chat about it, because you can just use one array, you can use two arrays, but with fewer code, because with one array then you have to kind of write special code for each, the P and the Q. But if you use two arrays, then you only have to write one code. So this is what I'm plotting against, because you could just write one finder for both P and Q and then just do like a common prefix type thing, right? And that's basically the idea. I think I'm going to do that. So let's get started. And I know that this is okay because, like I said, the lower bound is going to be at least linear time, because you have to look at the entire tree to find the nodes. And yeah, yeah, I think that's how I'm going to do. I'm trying to think about what's a good API for this. I think a good API for this is probably reasonable. Here's a node. Let's just say for now it will return a tuple, which has a flag found, a Boolean flag either is found, and then maybe the array that gives you the path. You can do it either way. You can maybe even use a like a variable outside the scope or something like that, but I don't know, I'm gonna play around with it. So node is none, you return false, whatever. Yeah, if node is equal to, oh, I guess I have to give the looking for, I'm trying to think about the name. Let's just call it X or target. Target is good. All right, target. I know that, so what I'm looking for right now, just double checking for a second, I guess they're unique, because what I was looking for is that, you know, this is a pointer equality check, and technically, unless you know what you're doing, you should not be doing that, or if you know your language, I guess depends on your language as well. So you can either do something like this, or you could just do what I did, because I think in this case it'll be okay because we're looking for exact node, or at least assuming that they give you the exact node that's already in the tree versus a replica of that, which I guess is actually not clear. So let's stick with that route to kind of make sure. Then we return true, and then no, say. Otherwise, if find node.left, okay, let's just go left is equal to find node.left. If left of 0, that means that if we found it on the left, then we return true. This is a little bit awkward. I think if you ask me, I would maybe have a class or a name tuple for this tuple so that it can be a little bit clearer, a little bit easier to use, and a little bit less error prone. But for the purpose of time, I am a little bit lazy, so this is what I'm going to do. This is the array plus no, or the other way around actually. Whoops, because we want to, okay, we also do it for the right. Of course we have to actually do the recursion first. And then otherwise we also return false at the very end if you cannot find it in the left or the right. And then now what's left is that we have to find the root of P and find the root of Q. Let's just call it P node maybe, I don't know. Naming is really hard for me. And then oops, or maybe P path and Q path. And then now we can just look for X, Y in zip of, okay, so for P node, Q node in zip of P path, Q path, if Pn.value is not equal to P or Qn.value, then we return the last node maybe, and then we set the last node is equal to just Pn, I guess, I don't know, root, because the root is always the answer per se, and then if this goes out of the thing, then the last one will be the last one. So I think this is okay. Maybe I have some off by one issues, but the idea is basically that. Talked a bit today about it, but I think this is I think the hardest part for this particular problem, oh, I forgot to search for something. I think the hardest part about this problem is just proving the lower bound perhaps, and if you're in an interview obviously, talking about the lower bounds and stuff like that so that you can kind of move on. At least that's what I would look for if I was an interviewer, because I think the implementation, once you get the algorithms down, is pretty straightforward, and if you are convinced that you can do whatever, then it's pretty straightforward. Is that the... This is a weird looking interface for the tree. Am I doing this right? I guess that's right. Why does it give me an unknown error? Dong dong dong, that's so ominous. Okay, so it worked that time. Okay, so does it have at least 2 nodes? Yep, okay. So I guess that's the thing that I would have looked for, is maybe do one node to no nodes. And this is linear time, as we said. We'll kind of go over it in a sec, but that's why I didn't really take a I didn't really worry about the complexity. This one doesn't really matter. They're just unique, right? And we don't really do any arithmetic. So let's give it a submit. And here we go. The last problem of June, done. So what is the complexity of this? Well, this is just a depth first search or pre-order traversal of the tree. So this is going to be linear time, and we do it twice, so it's still going to be linear time. In terms of, yeah, and this is also linear time because you can, in the worst case, and that's what I think about when I think about time analysis, in the worst case, you have just two linked lists and they point to the same node, or maybe roughly the same node. I don't know if they have to be different. I guess they have to be different, but if you have a linked list and they're like next to each other, but in a node, this is going to be linear time. But in either case, this is all going to be linear time. In terms of space, this is also going to be linear space because we put the path of the array here. I don't know. Well, the truth is you cannot actually do that much better because in the worst case, this find is going to take up the stack space, a linear stack space, again, using linked lists as we talked about. So yeah. Can you do any better in terms of space? Because time we proved the lower bound. Can we do it in all of one space? I don't know. Maybe. No, I guess not, because you still need to know parents and stuff like that. So I think that's always going to be a little bit tricky. Like even if you do some kind of traversal of the tree that is lower, you still, I don't know. Maybe I'm wrong on this one. Let me know in the comments, or if you looked at the comments or whatever. I guess we could take a quick solution look, but I don't think so. That's my guess. I'm not always right, so let's see if I learn anything new. Backtrack, okay. Yep. Irritably, that's what I was saying. Irritably without parenting. Okay, well, it's still, yeah, I don't know. Okay, didn't really read it that much, but I think these are the same ideas anyway. Okay, that's really all I have for this one. Let me go back to the code so you could take a gander. What? Okay, so yeah, that's all I have for this one. This is the end of the month. Hope I see you next month, which is tomorrow. Stay good, stay cool, to good mental health. Thanks for chilling and kind of do problems with me for this month. I don't know, I just enjoy doing it. So anyway, I'll see you later. Bye bye.